All right, solving the third problem for the dynamics review. We're given a graph of vertical position for an elevator as a function of time. We want to graph the velocity as a function of time based on this position graph. What you should remember is that the slope of position is velocity. So we can find sections of this graph that has a constant slope, for example, between 0 and 8 seconds, and then we can find the rise of that slope and the run. So the rise here, 12 meters. The run is 8 seconds. And find the slope of that. So 12 over 8 gives us a value of, this would be 3 over 2, 1.5. So we would have a constant velocity of 1.5 from 0 to 8 seconds, right? It's a constant slope during that section. It's a constant velocity during that section. Then it goes to 0 between the next 2 seconds. So from 10 to 20 seconds, we know the slope is 0. So we can draw that there. However, between 8 and 10 seconds, there's a change that happens. So you can see it curve here in the graph, which means there's a changing slope, and so the velocity must be changing from one value to another. Right? It's slowing down in this case, and so the velocity would drop down to 0. Same thing happens between 18 and 20. Right? From 18 to 20, it changes from a 0 slope to the slope between 20 and 25. So the rise in that case there is again 12 meters, and the run now is 5 meters. Okay, so 12 divided by 5 would be 2.4. Sorry, yes, 2.4. And so your velocity would be sitting somewhere between pretty close to 2.5 here. I did make a mistake. So this should stop at 18 seconds. And then from 18 to 20, that's when this change downwards happens. Right? So that would be our velocity graph, right? We have constant velocity during the sections of 0 to 8, 10 to 18, then 20 to 25. Those are all constant velocities. And then the sections from 8 to 10 and 18 to 20, that's where the velocity is changing. So you have that downward slope. You calculate the average acceleration from 8 seconds to 10 seconds. Basically, we just want to find the slope of this second graph, right? So from 8 to 10 seconds, the change here is 1.5, or rather, negative 1.5 meters per second over a span of 2 seconds. So the slope, right, the acceleration would then be negative 1.5 meters per second divided by 2 seconds, which would be negative 0.75 meters per second squared. I'm going to show the acceleration for this. Since the elevator has a negative acceleration like this, we would draw the acceleration downwards like this, right? We want to calculate the apparent weight of the passenger during this section here, right? Keep in mind that as far as free body diagrams go, what's happening is that the normal force is now smaller than the weight of the person. And remember, this normal force is what the scale reads, right? So to get that value, we need to set up a net force equation in the y direction. So we have the normal force minus mg is equal to the mass of that person times his acceleration, right? And so we have to solve this equation for the normal force. We know what the mass is. The mass is 70 kilograms. It's given to us in the problem. And we just solve for the acceleration. It's negative 0.575 meters per second squared. We can plug in these values. We can plug in g as being 10 meters per second squared.